Now let's explore calibration curves. Now we'll make a calibration curve out of some standard that, say we want to measure the concentration of copper in a sample. We will likely need a calibration curve for that, especially if we're using a spectroscopic method. So, or a method that shines light on something or reacts to how much light is coming off of a sample. So, an example of that would be atomic spectroscopy. Now, to do that, we'll need to measure the proportionality constant. So we'll have some intensity is equal to the proportionality constant times the concentration plus the blank. Now, when we do that, we'll have to make sure that we make a calibration curve. We'll measure several concentrations of several samples of known concentration, and then we'll create a calibration curve. Now, it's funny to say curve when most of the time we're looking for a straight line. But in fact, there are curves in our calibration curve. So especially at very low concentrations, we may not see any difference between a 0 concentration and some concentration that's a little bit more, right? So this would be where we're down at our limit of detection. Right? Once we get past the limit of detection, then we'll start seeing our intensity go up and we'll enter our linear range. Often methods have a linear range, and then that would extend from here down to the limit of detection. Somewhere down there is the limit of detection. So in between here's linear range. And then we'll have a portion of our curve that is a dynamic range. It's possible that when you get into higher and higher concentrations, that the curve is no longer linear. So it's important that wherever we're measuring our unknown, it is contained within where we've measured for calibration. Right? So if I only calibrate up to, say, this value right here, then I would not want to go very far beyond that value in my concentration, because the farther I go up from there to measure, I am going to encounter a larger possibility of entering a dynamic range which I may not know about. Now, if I have calibration points all the way out in this dynamic range, it can be still useful. You'll have to use a different formula than a linear fit to determine the concentration at those points, but it's possible to use it. And so it's not wrong to use the dynamic range, but it's important to recognize when I might be in it. So make sure that wherever you're actually measuring for a analytical method, you stay within your data points of the calibration curve. It's also important not to go below where your calibration curve is, so that we don't encounter the limit of detection. All right, so now that I've talked about some of the parts of a calibration curve, let's talk about actually making one. Now, sometimes an analytical method will specify exactly how to make a calibration curve, and it will detail what primary standard to use, how it's handled, everything. And sometimes you'll get to make those decisions on your own. So let's present a problem. We would like to have a calibration curve that goes up to 10 parts per million in copper, and probably down to about 1 part per million copper. So how could we make a calibration curve for this? So we want data points between 1 ppm and 10 parts per million. Now, we could attempt to weigh out 10 milligrams of copper and dissolve it and then dilute that into 1 liter of solution. But that would be inadvisable. For one, it's difficult to measure that low of a quantity accurately. In general, I would say don't measure less than 50 milligrams on an analytical balance and expect it to be very accurate. Preferably, you'd go more with 100 milligrams, or perhaps even a tiny bit more. We are talking about very small quantities of reagents, and especially when we're talking about copper, which is not an expensive element, let's go ahead and say the minimum we should weigh out is 100 milligrams. So if we were to try to weigh out 100 milligrams and then directly make this particular concentration from that, we would find that the volume required is rather large. In fact, that would be, let's see here, 100 liters, which is a lot. I think it's 100 liters. No, 10 liters. That's still a lot. 10 liters is, I probably don't have a 10-liter volumetric flask. So we don't want to do that. What we would rather do is have a much smaller volume. So let's go through a better way to make the calibration curve. So what I'm going to do is I'm going to weigh out 100 milligrams of copper metal. And copper metal is a primary standard. It abides by a lot of the other goals that we want in a primary standard. And what I'm going to do is I will dissolve this in a small quantity of nitric acid. So I'll use 1 to 2 milliliters of concentrated nitric acid. And if it doesn't all dissolve, I'll add a little bit more concentrated nitric acid to get it dissolved. Then I will quantitatively transfer this little bit of copper solution into a 100 milliliter volumetric flask. And I will dilute to the mark and make sure I have an accurate solution. And in doing that, I will have 100 milliliters or 100 milligrams of copper in 0.1 liters, which would be 1,000 parts per million. And I think this is where I had my earlier confusion where I thought it might be 100 liters. So I was thinking of this solution right here. But I'll have a 1,000 parts per million of copper. Next, I will dilute that solution by taking 10 milliliters of it and diluting it into 100 milliliters using a serial dilution. Now this will dilute it by 10, so I will have a 100 parts per million concentration. Next, I'll take this solution, and I'm actually going to use 20 milliliters of this. And I'm going to dilute it into 200 milliliters because I want a little bit more of this 10 parts per million solution. Because I really don't want just 10 parts per million. I want several concentrations in between 1 and 10. And so one of the ways to do that is to make a large amount of a stock solution. So I have a stock solution that's 100 parts per million that I could dilute from, and I have a solution that's 10 parts per million that I could dilute from. So next, here's what I'm going to do. I'm going to take 10 milliliters of this solution, and I'm going to dilute that into 100 milliliters, and that will make 1 part per million. And I'll have that, and now I have my 1 part per million standard. And then I'm going to take 20 milliliters and do the same thing. I'm going to dilute it into 100. And now this will make 2 parts per million copper. And yes, it's actually copper nitrate, but because I measured it out 100 milligrams of copper metal, it's actually easier just to say, 2 parts per million of copper metal. And then, yes, there's some other nitrate in there, but not important. Let's do 40 milliliters next. I could do 30 if I wanted to, and I could have 1, 2, 3, 4, 5, all on up. But I'm going to just go ahead and do 40, put that into 100, and then that will give me 4 ppm. And this is 10 milliliters of my 10 parts per million sample, 20 of that, 40 of that. Now, I'm going to come up and I'm going to take 30 milliliters of my 10 part per million sample, and I'm going to dilute it into 50 milliliters. And what this will do is that will give me 6 parts per million sample. And I'm going to do 40, and I'll again dilute that into a 50 milliliters beaker, or volumetric flask, I should say. And that will make my 8 parts per million. Now, look, I could have done 60 and I could have done 80, but then I would have had to make more than just 200 milliliters of this. So just keep that in mind. Sometimes when you're getting up to these larger amounts, you can go ahead and make the 50 milliliters of it. And we could have done that same thing here. We could have done 20 into our 50. Just depends on what you want to do. And then if we add all of this up, I should have used about 140 milliliters. Of course, there's always a little bit of loss. Somehow, magically, you end up using slightly more than that. But that will leave at least some, around 50 milliliters of my 10 part per million solution to use for that standard. So then I could just use this stock solution, but it's also my top standard. And so that's an easy way to make a calibration curve. Now, typically you do want to make some stock solution that is a higher concentration and then dilute several different volumes from there to make a very quick and simple calibration curve. Now, the amounts will vary, and how much I dilute and how much I make will be dependent on what you're actually analyzing and how the analysis goes and the requirements for that. But this is a reasonable example for how you would do that and how it functions and how the math works for it too. So that's a little bit about calibration curves and a little bit about how you would make a calibration curve from a primary standard.